Welcome to Engineers Ireland and the Junior Cert Maths Grinds. Today we're naturally following on from what we covered before, and we're now going to deal with quadratic equations. And fundamentally, a quadratic equation can be written in a general form. You will notice as we head towards the end of this chapter that this general form, I will often refer to it as the general form, but you need to see it and to understand it in your mind, because the equation for solving them later on relates back to it. And this is the map. This is the thing that makes that equation much easier, or how to use that equation much easier. The general form. First thing you have to understand, the word equation means something is equated to something else. This thing is being equated to this thing, which happens to be a zero. The second thing you'll notice is that we have a free term here, something that is not multiplied into any version of x. We have a linear term, which is just x to the power of 1, which is itself, and you have some coefficient in front of it, which can be any number, including 0. For example, our quadratic equation could be and that really, as you know, so b can be 0. And so far, this amount of it is the equation. That's a line. 5x plus 3 equals 0 is a straight line. What makes it a curvy line rather than a straight one is this bit, ax squared. In the example we've picked there, the a would be a 5. It's the coefficient of the x squared. And what they look like are the ones that you generally will be using for in your Junior Cert. They look like that. Or they look like that. A lot of work was carried out on these back in the Middle Ages by the Arab world, North African Arab world mainly. The advances that were made were so significant that probably the most formative book of mathematics in those times was one written by an Arab mathematician. The book has got quite a long name, but part of the name was algebra, and it continued on. And our term algebra comes from the title of that book. It's very difficult to appreciate now how even small steps in the earlier mathematics, how important they were, and in particular how hard it was to find these little steps. We have a huge debt, obviously, to the old civilizations, particularly the Greeks, who, in my opinion, distilled a lot of the stuff that the Egyptians would have had, that the Babylonians and others had. And they saw behind the rules that others had, and found mathematics. The pure maths that we really have built a lot of our sciences and engineering on. There's a middle step before you get to what has been taken up by the Europeans, and that middle step was mainly carried out in Arabia and in the southern half of Spain, which was Islamic at the time. The Moors had taken over the lower half of Spain, and it was through the colleges in the lower half of Spain which accepted in Christians and Jews. They were very, very open-minded, and they taught them much of the mathematics that we know. It would have been lost to us if it hadn't been carried on for quite a number of hundreds of years and added to and improved by the Arab or Islamic world. So there's a huge debt that we owe there. Work on quadratic equations was one of the big areas. But anyway, that's a little bit of background. You'll be very familiar with solving quadratic equations by finding factors. We covered that in the second one, but there's no harm in just looking at one little example so that we can move on. If we're looking for factors, we are saying that we expect to get something like x plus a, whatever it'll be. I'll use different letters just to avoid confusion. Don't know if you know this one. That's alpha. And that's beta. They're the first two letters in the Greek alphabet. Because of our huge debt to the Greeks, we very often use their letters for things. And we're saying, if I have this in factors, it's going to, or is likely to look like this. And especially because there's only a 1 here in front of the x, it will definitely look like that over here. So if it's going to look like that, let's multiply it out. And what we get from that is x squared plus alpha plus beta x plus alpha beta. And that's the key. What we're saying is the last number here is the product of these two. And we're saying that the number multiplying into the x is the sum of those two. When we discussed this, I was saying to you, the first thing you're going to do when you look at your equation is you look at your signs. This one first. That's a minus sign. How do you get a minus sign when you know you've multiplied two numbers together? One of them must be minus, and the other one must be plus. Because plus multiplied by plus is plus, and minus multiplied by minus is plus. Only minus multiplied by plus gives you a minus. So we're certain that either this guy or this guy is a negative. Having looked at that, we're now going to look at this sign. That sign tells us that when we add the two together, we finished up with a negative number. So of our two roots, or sorry, our two factors, the negative one is the big one. So let's look at 14 now. And we're looking for combinations of 14. We know one is going to be positive and one is negative, but because this told us, because it's minus, that the negative is the bigger one, let's look for it. We're going plus 1 minus 14, and we'll say plus 2 minus 7. They're the numbers we're going to multiply and also add. This is the multiply column, and that's the add column. If I multiply these two together, I'll get minus 14. If I multiply these two together, I get minus 14. So that's correct. Now let's add them. minus 13 minus 5. This is the right line because we got minus 5 like up here. If we want to find, what we're now saying is that that is exactly the same as this equation here. And we want to find out the values that solve that equation. We can now say that implies x plus 2 equals nothing, or x minus 7 equals nothing, which means x equals minus 2 or x equals 7. Just to confirm one little thing for you. If we have two things, any two things equal to 0, the only way that can be is either x equals 0 or y equals 0. 7 by 0 is 0. 0 by 9 is 0. One of these must be 0, otherwise the answer isn't going to be 0. That's the exact same reasoning down here. We know that those two equal 0 because that's the equation we have dealt with. So x plus 2 must be equal to 0. That's why we've written that there. Or, and that's why we have or in here. It's not x plus 2 equals 0 and x minus 7 equals 0. It's an or, one or the other. The other option is x minus 7 is equal to 0. In mathematics, we've already discussed, naming things is a key way of simplifying things. And there's a lovely example in quadratic equations, and it has to do with related quadratic equations. So what are those things? Let's pick the example in the book again. The example one says, solve that equation and use your result to solve another equation. The other equation is your job is always to look and see what's there. What you have to recognize is we have something. It may be called y minus 2 here, but you can call this thing anything. You can call it Fred, you can call it Z, you can give any name to this you like. What you're recognizing is that this is exactly the same as that thing. And let's just for the moment call it Z. And now we can substitute Z every time in. Right? Now you can see that I have Z squared, the same way as I have an X squared. I have minus 7 of these Z's. Oh, it's the same as this. And I have plus 10 equal to 0. That's basically that equation, just with a different name. If this is the same as that, this one even though it looks much fancier because it's a y minus 2 squared minus 7 y minus 2's plus 10, it may look more complicated, but it isn't. This guy over here, the more complicated one, relates to this one, and that's why they're called related quadratic equations. We can easily solve this. Remember, the plus here means that both numbers, for example, that one and this one, they're either both positive or they're both negative. The minus here tells us that they must both be negative. So immediately what you would have been able to do is this. That told us they're both positive or negative. This told us they must both be negative. So we've got that far. And now all we're looking for is two numbers that multiply together that will give us 10 and added together will give us 7. We don't have to worry about the sign now because we've already decided the sign. Okay? We've separated it out as a different little problem. And obviously, it's the 5. Oops. And 2, which we already had. How can x minus 5 multiplied by x minus 2 equal 0? It can only be if x minus 5 equals 0 or x minus 2 equals 0. How can x minus 5 be equal to 0? Only if x equals 5. And similarly, x minus 2 can only be equal to 0 if x is 2. That has solved that equation. And we're going to use that information to solve this equation. We have decided, or recognized, we have recognized that x here has the exact same role as in this other equation over here, y minus 2. So we can say y minus 2 is basically the same as x. It relates to x. So what values of x? Oops. 5, see it coming down here, or y minus 2 equals 2, coming down from here. Easy. It just requires you to open your eyes, see what's there. Don't be afraid to rename things. And the other thing is, as you're going through, even if you are making what you would call a mistake, I don't call that a mistake. What you're doing is, if you're using your thinking system, you're playing through a number of fairly obvious things to look for. If it turns out the first one wasn't quite right, so what? You will find it in the second or the third one. The important thing is, if you're thinking, it's not a mistake. It just didn't turn out to be the right thing. And you just move on. You find eventually the right version. I'm stopping for a moment just to remind you of something. We've only really covered about 2 ideas so far in this section. So it's easy to understand this. But your half of the contract here is to turn understanding into knowing something. And you know how cocky you are when you know something. That's how you're supposed to get. Well, the only way to do that is practice. And in these books, there are lots of exercises. They're not there to make you feel miserable on a Friday night. They're there so you can turn understanding into knowing. It's only a few months from now. that you will be standing outside the door of your first paper in Junior Cert Maths. If you're standing out there knowing the stuff, having practiced, you will be confident. And at that time, standing outside the door, you'll be really thankful to yourself if you have actually practiced, worked on the examples, and turned understanding into knowing. Because you can go in there and perform because you're waiting to do so because you know your stuff. I know this is a very cocky statement. It'd be much nicer to have to say that than to be, I'm not so sure. It's all down to practice, and only you can do that practice. And when you're going through the questions, keep your mind open. Look to interpret, rename things, play with things, and you play generally over on the right-hand side. Okay. We've already looked at fractions, which are called rational expressions. They come up in quadratics also. The example. The important thing to know here is this is the kind of thing you've been doing since national school, and even in national school. You are well used to solving that kind of a problem. If you remember, you give yourself a simple problem to set up a map. That didn't take much. There's no reason then why this should take any more time. Why is it that the stuff on the right seems easier than the stuff on the left? The only reason is we know all of these things over here. We know them as a number. And here on the left-hand side, there's something that we actually don't know. We don't know the answer to it. But we can give it a name. We can call it x. And because of that, we can play with it as though we know it, a bit like knowing the 2 over here on the right-hand side. Our job is to ignore the fact that you don't know what it is and play with it like this. This side here demanded that we put something underneath the line here and stayed with a fraction. We're dealing with something a little bit different on this side because there's an equate. We have an equation. So I can multiply across, and so long as each term gets multiplied, we're happy. And we want to multiply by something like the 3/7 here, which is going to be 3x. We'll multiply across to simplify everything for ourselves. And it will be the same as you would have put underneath the line here, so it's 3x's. So we're saying 3x outside of pretty obvious that that'll cancel. It's pretty obvious that that'll cancel. And you've got I know it would have been very easy to go from this all the way down to this one. But there's no marks for being a hero on these things. Put in the middle step. Keep your mathematics simple. If you keep it simple, you actually stay running fast. If you start to hop, you introduce error because you're starting to think too much and do too much processing in your mind. put in your middle step. So we're looking at this now. And we get to a quadratic. Well, we might as well solve it while we're at it. There's just a single 1 multiplying into the x. So we already know it's x, x. That's a plus. So the two values are either going to be pluses or minuses. When they're added together, we find we got a minus. So we know we've got a minus here and a minus here. Now we only have to think in terms of numbers. We're looking for two numbers that multiplying together will give us 36 and adding together will give us 15. 12 threes are 36 and 3 and 12 are 15 equals 0. So we can say now we're getting and moving on to using the equation that most people, I think, remember many, many years after they've left school. This is probably the most equation they remember, which is the one to solve quadratic equations. Please put in this first step. I mentioned it at the start of this talk. You don't have to write it as formal as this, but at least write out the equation. That's the general form of the quadratic equation. It's the general form because we aren't told what multiplies into the x squared. We're not told what multiplies into the x and what is the free term is. So we've given them names. Those numbers are coefficients. They're constant. Each of those is a constant. And that's why we use ABC, constants. Generally, A, B, C, and if you have more of them, you go D, E, F. Whereas if you recognize variables, that's things that can change, have many different values. We normally use ones at the end of the alphabet, not the front of the alphabet. That's convention, and it makes life easy for us because we can look at an equation like this and we know that we have one variable, which is x, and 3 constants, which we don't know. Now, given that general form, we can state, and I'm deliberately putting in it, that implies, if we have this, that implies that x is equal to minus b plus or minus the square root of b squared minus 4ac all over 2a. Do you remember I've said to you before to be extremely careful about how you speak your mathematics? In this equation, there is one little secret word that you have to say. X is equal to minus b plus or minus the square root of b squared minus 4ac all over. It's not over 2a, it's all over 2a. That means that line extends the full length. I know this equation is in the logbooks, but if you get into the habit of just ignoring or not learning off equations just because they're in the logbook, You will spend a huge amount of time in your exams flicking back and over to different pages in your logbook and copying down the value from your logbook and then checking to make sure you haven't got it wrong. All of that takes time. And that's something that's in limited quantity in your exams. What you want to do is to avoid anything that wastes time or is just not effective. Learn these things off. It's well worth it. The other aspect of it is, it's like 1 and 1 is 2. I didn't have to calculate that 1 plus 1 is 2 because that's so well remembered from national school. I've just recalled it. In the same ways, I know this equation and a whole lot of other ones exactly the same way. I can recall them. So there's almost no wearing down or tiring of the mind in doing this. Whereas in almost any other system, if you do not learn things well and store them well in your mind, it wears you down, it tires you. And remember, in any given day, the likelihood is you have 2 exams. Morning one and evening one. If your paper 1 maths is in the morning, you do not want to be tired at the end of it because you've only got a short break on the second paper. You want both papers you want a good chance in both papers to get the marks you can get. And how you do that is follow systems that don't waste your mental energy. Learn these things off, but learn them carefully. The wording that you use when you're describing this equation, the x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. The wording is really important because if you get that wrong, you get your maths wrong. Now then, this is an easy equation. So let's look at an example. The first one that's given in this book. And the ways the examples are given in this book, it now says to you, oh, A equals 5, B equals 7, and C equals minus 3. You're expected to write this over on the side. Why? Because the ways this example continues, it starts straight in with x equals minus b plus or minus the square root of b squared minus 4ac all over 2a. Because that equation got written straight out, you are supposed to write this over here. Now, I don't think that's particularly sensible or fast. I think it's much better to do it this way. You always write this one first, then you write this one. I find, well, everybody has their own method, but I actually find that that is the easiest way to do it. Let's say general form. Now, when you were very small kids, 2 years of age, you probably had one of those big plastic red buses, the ones that had triangular holes, square holes, star-shaped holes, circular holes in it, and you had a matching set of shapes. Probably the first one of those might have only had 4 different things, and it took you a long time to work out that the square goes into the square hole. But once you knew that, it became terribly simple. Here, and the whole reason why you write down something like this is your little red bus thing. This is the big plastic thing with the holes in it. And what we want to do is to know what to put into each hole. There, there. What do we put in? Well, because you've written this equation here, the general form, you know exactly what goes into it. You're saying, I have B is this guy, etc., etc. So you write them all in. minus 7 plus or minus the square root of 49 minus 4 by 5, right? And it's minus 3. It makes very little difference if you make a little mistake, so long as you keep watching and you correct it. Again, because it's a minus number over here being put in for the c, put it in a bracket. The reason you put it in a bracket is you don't want to have to deal with the issue of what happens with this minus in relation to this minus. Shove it in the bracket, deal with that in the next line. One other thing, and by the way, this is a very easy example, but for more complex ones, this is a good system to follow. Remember this important right-hand side of the equation, or of the page. When you get a big equation like this one, with lots of stuff at the top and sometimes a lot of stuff at the bottom, don't become a hero again and try and solve it all the way down along here. You bring the difficult bit over to the right-hand side. And we would say, okay, 49 minus 4 by 5 by minus 3. And you can deal with your signs. Minus by minus gives us a plus. I'm taking more steps here than you need, but I'm taking the steps so that you know that if we are multiplying, for example, minus 3x by plus 4y, we're going to multiply those two. You don't do it all in one go. You deal with your signs. Then you deal with your constants, which are your coefficients. Then you deal with your variables. So it would be minus by plus is minus. And you go, yes, I've dealt with my sign. And you'd write down minus. Now you look at your constants and you multiply one by the other. It'll give you the constant bit. And then you deal with your variables. You multiply them together. So you separated out each little step. We know this is 49 plus 60. And now you can bring that answer all the way across. You can see this implies that x is equal to minus 7 plus or minus the square root of 109 all over 10. And now life gets easy. The important thing here is when the equation gets complicated, like this equation has, you take it in bits across on the right-hand side and you deal with each bit. As it turns out, we only had one difficult bit. That was the only difficult bit, so we pulled it over here. If it turns out what was underneath the line was also difficult, you would come along and you'd put it in here, putting in some sort of separator, then you'd look at that. Sometimes on the right-hand side of your equation, or of your page, you could run down almost the whole page. And the answer to your question might only go down 6 lines, 12 lines. Don't worry about spending a lot of time running down the right-hand side dealing with things. The examiner will be extremely pleased with you because you finish up with very nice, simple, clean mathematics down this side and can follow it down. If it turns out that you made a mistake, the examiner will look at what's over on the right-hand side. And the examiner, finding a small mistake over there, will then understand what happened on the left. It isn't nearly as hard for them to look through something like this than a big mess that would occur down on the left-hand side. Pull bits over to the right-hand side, simplify them, parachute them back into the next line on the left. That's the easy system. we are close enough to finishing this section now. What we're going to look at are the kind of problems that you get given that finish up with quadratic equations. When we were dealing with simultaneous equations, we also finished up towards the end of that section, that chapter, with a yappy language problem, which you had to translate into mathematics, and you finished up with simultaneous equations. We're going to do the same thing now, only we finish up with quadratic equations. And there's one little rule that you just have to remember to make your life easy for yourself. Let's look at 400 divided by 40. And we'll also look at 400 divided by 20. This one. What do you get out of that? You get 10 out of it. This one, you get 20 out of it. You'll notice that the same number is being used on top in both of these cases. That's just to keep this as a simple little problem over on the right-hand side. And you can do this yourself, okay? Just to clarify in your mind. With the same number on the top, what we're looking for is what happens if I have a bigger number underneath. See, the 40 is bigger than the 20. When I have a bigger number underneath, I finish up with a smaller answer. The 400 divided by 40 only gave me 10, whereas when I had the smaller number underneath, the 400 divided by 20 gave me a bigger answer. So, something divided by big, and the other option is the same something divided by small. This one gives me small. This one gives me big. You just need to know that little, basic little thing. Now, you need it so that you know how to set up your equations. Let's look at the example 2 here. This is page 49. And we'll hear what the question is. A prize fund of €360 was divided equally among a certain number of prize winners. We haven't been told how many. We can give it a name. We can call it X. So X of them got 360. Now, this is where the little puzzly bit comes in. If the number of prize winners had been reduced by 3, if there were 3 less, that'll be X minus 3 of them, of course, whatever number that is. Each share would have been €10 greater. Okay. If X represents the number of prize winners, write an expression in X and hence find its value. That's a lovely little question, and it's very typical of the kind of things that come out of this. So, case 1. X winners. Case 2. X minus 3 winners. The total amount is 360. So each gets 360 over X euros. Over here, each gets 360 X minus 3. And we are told that in this case here, these guys would have €10 more than these guys. So what we have to do now is to recognize how you just simply write that down. These guys are getting €10 more than these guys. And we were saying, €10 more than those guys. So what these guys got plus €10 is equal to what these guys are getting. Case 1 plus €10 equals case 2. As long as you can keep using the language, keep using, in this case obviously, keep using the English of the problem, so that you're absolutely clear when you step through your equation that you have interpreted what you're told. The money that they'd have got in case 1 and another €10 is what they'd have got in case 2. And that is what it says here. If there was 3 less people, each share would be €10 greater than in the first case. So we are okay there. And that obviously can be simplified. Again, we can happily multiply across by x multiplied by x minus 3 and simplify. And the whole thing is going to come down to, because in between what we've written here and this next line, there will be a number of lines for you where you carefully step through your multiplying across business. And you will get this. And that has given you a quadratic, and it gets solved. The real point here is exactly the same as the point in relation to the simultaneous equations. You have a little problem in the physical world out there. Your job is to interpret that into mathematics. And having interpreted into mathematics, your job is to use straightforward techniques to solve it. It's not difficult. The important thing is getting from the yappy story to your equation and doing it accurately. And you'll notice I've deliberately written above the equation something that is a halfway house between the long yapped out question. It's case 1 plus €10 equals case 2. Having written that, I feel more confident in writing my mathematics. The type of problems that you do get generally involve 2 scenarios, and almost all of them involve something divided by a number and something divided by a different number. And just recognizing which should give you the bigger answer, that's why I gave the little thing at the start, is the only little thing you need to keep in your mind, other than your standard quadratic equation and the interpretation. Just wondering if there's any particular one here that we can pick on that'll give you a good insight into this. This one will do very nicely. And we leave it after that. Page 54. Question 22. Because this brings back in the whole thing of time, distance, speed. The boat traveled 80 kilometers up a river. Okay, we'll say the distance is equal to 80 kilometers. And it does it at a speed x kilometers per hour. That's going up. That's case 1. You can use different names. I don't mind, so long as your mind feels happy with it and you can step through a process of turning English into mathematics. If it works for you, that's fine by me. What's the case 2? On the return journey, that would be going downstream then, what happens? The speed was x plus 4 kilometers per hour. So if on the way up, for argument's sake, he was doing 20 kilometers per hour, on the way back he'll be doing 24. It's just 4 more than he had done on the way up. We don't know how much he did on the way up, so we can name it x. And now we can play with it. We get questions now. First question. What was the time taken for the journey up the river? Okay. Time taken. Distance. Sorry. And follow the process that I mentioned to you before. Speed. Think of any speed. 5 kilometers an hour. And just drop away the number. So it's kilometers per hour. You'd say, so speed is equal to distance over time. And we know from the previous example that we covered that we can manipulate this equation and say time equals distance over speed. So now we're in a position to set up the equation. We have it in terms of time here because we were asked for time here. So what was the time taken for the journey up the river? The distance was 80 and the speed was x. Notice that we're looking at kilometers per hour. So we're dealing with time here. This is hours. What was the time taken for the return journey? That's our case 2. They're 2 times. Now it's saying, if the difference in the time was 1 hour, find the value of x. The difference is 1 hour. Which of these do you believe will give you the biggest answer and the smallest answer? That's why we did the little problem at the start where we said 400 divided by 40, and we'll find that, oh, well, that's 10. Here now we're looking at 400 divided by 20 and saying, that's 20. The smaller number underneath gives us the bigger number. X is smaller than x plus 4. This gives us the bigger number. It'll give us the biggest amount of time. Think about it. You go at a certain speed. What if you went at 4 kilometers an hour faster? It should take less time. So we can say that 80 over x, that's one of the things we want to do to set up our little time problem. We're saying that amount, that's going to take longer, okay? So the other one is the smaller one. We're now saying the smaller one plus 1 hour equals the bigger one. Is that sensible to you? It has to make ordinary reason sense in your mind. We're saying case 1. This is case 2. Just to keep your mind clear, you can write in as many little things in this as you feel like it. We've just said the smaller number underneath will give us the biggest one. So we're saying big time equals small time plus 1 hour. Because that's what they're telling us. Having done that, you've actually done your maths, your conversion. You've converted from a story in language into a mathematical equation. All you have to do is simplify the equation, and solving it is a matter of straightforward quadratic equation, and you solve. Once you get to this equation and you simplify, you've no problems. The real issue is to set up some little game plan like this. A case 1, you know the distance, and it's going to be the same for both. You know the speed, and you're saying, yes, that's going upriver. Then you're looking at your case 2. Now we're saying, the questions then are the little things you look for. So time taken. You go over here, and you just simply say, I can walk at, we'll say, 5 kilometers an hour. So my speed would be 5 kilometers an hour. Or you can say, a car can do 30 kilometers an hour in town. Speed equals kilometers per hour. Once you set that up, you play around with it to put out here the thing that's been asked for over here. Time is distance over speed. Time equals distance, see up here, divided by speed, see up here, speed x. Oops. So we've set it up, and we know it's ours. One last little thing. Having solved this, having found out the answer, x represents what? A speed, doesn't it? You're told it's in kilometers per hour. Because of that, When you get an answer, whatever the answer is, let's just say 20. If you write down 20, you don't get all the marks. When you're given dimensions, you must, as part of your answer, give a dimension for it. In the same way as when you're dealing with areas and volumes. If they say so many centimeters in one direction and so many centimeters in another direction, the area is centimeters squared. Here we have been given dimensions, so we know time will be in hours, distance is kilometers, and speed is kilometers per hour. So it's part of your answer. Okay, we'll leave it at that. See you the next day. Bye now.